Welcome all to the second part of the series session, second part of actually my data series session, where initially we had discussed around understanding the concepts of the data. However, in this session, we'll be continuing that particular series only and talking more about data, and we'll be covering aspects of dimensionality reduction, which is again an important aspect that when you have to consider when you're transforming your data for any machine learning use case. I will be presenting my screen and all right. So the agenda for today's session around dimensionality reduction is understanding what dimensionality reduction means, what is actually a data dimension, how do you interpret data dimension, does it tell us anything about the data complexity that we are dealing in, and then talking about what are the benefits, although there are as well limitations to that also, but that we'll cover when we are talking deep into principal component analysis and factor analysis. So I'm covering these two aspects majorly because these are the two most used techniques and the most sophisticated techniques when we talk about dimensionality reduction. So PCA and factor analysis are most widely used when you have to reduce your data and you don't have to deal with multiple lines of code and multiple algorithms that you need to create on your end. So this is a predefined algorithm that is available out there. It is there in multiple Python and R libraries, so it's freely available and it is easy to interpret as well. There are some niche limitations to it that we'll be discussing in this session. There's certain best practices that I also want to cover around. It's based on the experience that I have gathered and the best use cases that I have dealt with, which will help you in understanding these two algorithms better and not make the mistakes that generally people do while handling these algorithms. Then we can have a brief Q&A if time permits. Um, so yeah, moving into the session, talking about dimensionality reduction. From my last session, I will take some pointers from there. Whenever we are dealing with a large chunk of data, let's say we are dealing with a web analytics data, which is recorded every session, or a patient level data, or a retail data that captures any transaction of an e-commerce website. This is a huge amount of data and primarily captured every minute that we are dealing in our day-to-day life. So to compress this data and to make it into a usable form, we need some kind of approach that helps us in reducing that. And then computationally, it is easier for us to understand the data better, visualize it in a better format, and even the best use case is develop a better model out of it as well. So if we look at any generic data in our day-to-day life, we have hundred of columns. If I talk about an image data, if I transform that into a numerical format, it will have thousands of columns. Similarly, if you transform a raw textual data, it can again have the number of, if you assume number of words as your column, then it can again have hundred of columns there as well. So there is always a need to reduce them to a concise form, that those concise two, three variables tell us the entire story of the data, and we don't have to uh, he- uh, run our head around all these hundred or thousand columns that are there in the data. Also, it becomes easier for us to store the data as well whenever we are running any algorithms on top of that. So this is one of the major aspect, that whenever you're dealing or working on your local system and people who are new to the data science field and don't have a sophisticated system at their place, it is always beneficial that you go use such approach that helps reduce the size of the data, which in a way will help you use the data more holistically. So these are certain pointers that helps us in reducing the dimensions and as well as the increasing the usability of the data. On top of that, it also takes care of the multicollinearity that we usually have an assumption when we are dealing in regression scope. So it also takes care of these aspects that we usually try to take care when we are cleaning the data. So these, it actually takes care of all those related variables together and kind of group them together. So that's one aspect of it. And whenever you have data with thousands of columns, you cannot have one view of that particular data. You cannot visualize it in a 2D format. If the dimensions are even more than three, then also it's very hard to visualize any kind of data. We can actually visualize data in a 2D or 3D format, but when there are thousands of dimensions, it's very critical for us to know how to we can reduce it so that we can visualize it in a way and make sense out of it. Now, talking about the most frequently used data dimensionality reduction techniques, there are two major techniques that people most frequently use and are widely respected in the industry as well, because the output that they generate is much more accurate or is much more easy to understand than there are the other techniques that are there available. So diving into principal component analysis, a brief overview of how these two techniques are different. We first need to understand what they actually do. So assuming that we have a large set of independent variables in our data, and there is an aspect to this that both these techniques are unsupervised. There is no dependent variable out there. So we will consider these two techniques in an unsupervised way of learning. And then what they give as an output is something that's like something like how we interpret a linear equation. So if you talk about PCA, it's like if a group of variables is reduced down to, let's say there was a group of 100 variables in the data, but we reduce down to 2 or 3 variables. Now, doing this exercise, we are not losing any explainability or the variance of the data. The approach of PCA helps us in maintaining whatever variance was there in the data and actually holding or maintaining around 90 to 95% of that variance. So basically, we can assume there is very less information loss, or the information loss that is even happening, which is around 4 to 5%. That is something that will not have a significant impact on your output as well. So you can assume that fairly I am dealing with the data that with your entire data that was in the original format, even after running PC or factor analysis. So first thing about PCA is, in general approach, our independent variables are concise to a smaller format in a group of, let's say, 1 or 2 variables. Now in PCA, all the variable information will be part of the components. When I say that, I mean that PC1, let's a component out of 5 variables, I'm creating them into 2. All the value, all the data variance that is there in these 5 variables will be captured in one component. Similarly, the other component will also capture some amount of data variance of all these factors. And one thing to note, that these are always orthogonal to each other. Like basically, if we imagine them in a 2D space or anything, they're always perpendicular to each other. So let's say if PC1 is pointing us in X direction, PC2 will always point us in Y direction. So they do not have any codependency on each other. And that is a basic assumption that we have to consider when we are building a regression model also. Talking about factor analysis, let's say we had again the group of 5 variables. But in factor analysis, one factor would be created by a group of some variables only. The impact of other variables on that factor would be negligible. So what it helps us is, it's a more interpretable form than PCA, that what this factor is actually signifying. So let's say these 2 variables were hinting at something. This variable is an inference of what these two things are combined telling you. So that's what an interpretation of factor analysis will tell you. And obviously there is some error associated in factor analysis that we'll delve in when we go into our further slides. Now, talking more about principal component analysis, as I initially mentioned, it's a way of reducing our large set of variables into a smaller chunk. These variables could be linearly correlated to each other in the original format, but what we get out is an orthogonal variable, which is perpendicularly related to each other on the axis, and there is no linear relation between those two variables. Now, to understand how this particular thing approach, we can assume an m-dimensional space of data points. All these are scattered in a 2D space. For the sake of the example, I've currently taken a 2D plot here to understand how PCA is actually working. And the main idea is that we keep intact the variance of our data, because that is the essence of our data. And if you are building a machine learning model, that is what something you want to retain. Because let's say if you have no basic understanding of what all the fields are in your data, and there are huge set of variables, you want to drill it down to a certain extent and create a niche model, let's say, out of it, or a first draft of a model out of it. So these are the basic steps that you can use, basically having a PC on top of that to reduce the number of columns and build a model on top of it. So that will keep the essence of the data as well, and not cause any loss of information on this. Now let's assume I consider 2 categories of what was the percentage of men and women in a particular area. Now I have standardized this data to plot it on a scatter plot. And this is across a particular region that I have captured this data. But my main hunch is that can I represent this data in terms of one equation or not? So that is the goal of PCA, that we basically create a component out of all the columns that are there and represent it just by one component. So what I am trying to do here is, in if you look at this particular data, it is not, it's a raw format. These are percentages values on both the axes is standardized. And then I have to shift this particular data to an origin center. Now, this is a basic assumption when we are running a principal component analysis, that the first is our data should be standardized. Basically, the mean should be either zero or close to zero. Now, what that helps us is that we can plot our data in a quadrant format. And when we do plot our data in a quadrant format, it becomes much more aligned and much more clearer for a mathematical model to interpret it. Now, our basic idea would be that we are able to fit a line that caters to all these points. Now, when I'm saying catering to all these points, it basically is the maximum square distance from the center point. So let's say if I'm assuming a particular point on the second quadrant, the maximum distance that is there from the origin is when I can say my variance is maximum, explained that by that particular line. So this third image basically tells you that when a when we when we are trying to get this best fit line, the model actually starts by a rotation, and it finally ends its rotation when it finds the best suitable point where you are able to achieve the maximum square distance for all of these points. And when you are able to achieve those maximum square distance for all of these points, then we say that we have a component created. So basically, when we say this particular line, when it holds flat, it is the point when we can say a component is created or a best fit line is there that is created. Now, a singular point, like basically one step distance from this is basically, or the direction of this basically, this of this particular line is called the vector. And this vector in this particular scenario or mathematical interpretation is an eigenvector. And the values of all these small data points that it has in it, so you can assume it's a long vector, and it will also have a projection or a value interpretation of all these small data points that are there. Those values are nothing but eigenvalues. Moving to the next slide. Now, what I was showing you till now was a very basic approach in which you have only one or three, four columns in which there is one categorical column you want to understand the interpretation. But when we are dealing with a large chunk of data, it could be an n cross k metric, it could be any dimension data. It's a huge chunk of data, and we always solve these kind of problems in a matrix multiplication approach. You can read about single value decomposition also, which is the basic crux of how PCA is done. I will be talking about how matrix calculation happens in PCA, and it is based around what I was talking in the previous slide only. It is how a particular vector is created. It is the steps that we were following in that particular graphical approach. When we talk about in the matrix approach, how we can relate to that. The basic aspect of developing a component out of a set of 5-6 variables is that we decompose those variables. Now, decomposing variables can only be done through matrix multiplication, decoding what is the main essence of that matrix and only creating that matrix output, which is important, and Kate covers all the values of the different columns that are out there. So what I say here is the PCA can be determined by eigen decomposition of the covariance vector. After all, the geometrical meaning of eigen decomposition is to find a new coordinate system of eigenvector through rotations. So as we were seeing in the previous slide, the rotation of that particular best fit line was telling us where it should stop and where the maxima is attained, and that is the point where a component is created. Now let's assume for an example we have a data which is n cross k matrix where n are your number of rows and k are your number of columns. So first, my first job is to standardize the data or create it in the mean centralized way. And the best way of doing that is, let's say x, I represent my data with the name of x. Now x mean x var will x minus x var will be a standardized format where I'm subtracting each of my value with the mean of each row. So each row, if I assume the first row, the mean of this row will be subtracted from each element of this particular thing, and then whatever we'll have is a standardized mean centered data. Now, when we have this, if you remember covariance, how we understand covariance is nothing but the relation or a variance, randomness between two variables. Now we have set of n k number of columns. Now when we have to understand this kind of thing, we will be multiplying each row and understanding what is the variance of the entire data. And that can only come out from a covariance matrix. So what I'm trying to do here is, let's say B is x minus xr, which is nothing but the original data minus the mean of the data. I will be multiplying this data with its own transpose. So this particular B transpose into B is nothing but creating a covariance matrix. Now this covariance matrix will be n cross n, right? And what it actually gives me at the output is the entire variance that the data process, like each data point in this particular matrix or the original data, what is the entire covariance. When you have the entire covariance matrix with you, you can actually decompose into different matrices, which will give you eigenvectors, eigenvalues, and how the particular covariance was created, right? So if let's say my C covariance matrix was created here, and I do an SVD decomposition. When I'm saying single value decomposition, it means creating single unitary value matrix out of a particular matrix. So I have a complete covariance matrix which has values in all of these fields. I have to create three different matrices out of it, which are single value. By single valued, I mean most of them are of nature of unitary. Basically, when I say a matrix is unitary, it means that if you multiply it, just like how I multiplied this here with its transpose, it will give you 1 as the output. So that is when you say the matrix is unitary. Now, when I decompose these matrix using SVD decomposition, it will give me a Wn cross n matrix, which will have eigenvectors across each rows. And again, it will also give me a diagonal matrix, which will possess the eigenvalues of these. Now we don't have to use the entire matrix now. What the algorithm does is it picks the only most important vectors and most important eigenvalues. For example, the most important eigenvalues are usually greater than 1. So we consider only those eigenvalues and create a data which is nothing but I have this vector matrix out. I have to multiply this with my original data and I'll get something called a component. So I am picking each vector by vector, and it is on me how many components I want out of it. So it is a bit complex to understand, but this is the mathematical backend of PCA, what is going behind. And it's in the matrix format is the most easiest way to understand how the mathematical flow of PCA looks like. So to give you a quick recap, what we have done is we first took our original data, we standardized or we subtracted it with our mean, then we developed a covariance matrix, then we had to decompose our covariance matrix to basically create a matrix of vectors and eigenvalues. Now eigenvalues is nothing, if you multiply to matrix with its transpose, you will always realize that diagonal always represents the sum of squared distances. Now this sum of squared distance is nothing but what we were trying to maximize in this particular approach also. Whenever during this decomposition exercise, it's a iterable exercise, and whenever a maxima is attained, that is when we say the matrix has been completely single decomposed into its unitary matrix, and there is the point when it stops. So that is when we can say that we have an eigenvector matrix out, and using that we can primarily create our principal components. Now the second aspects that come is what is the right amount of components that we should pick in our data. Where is the point where we should stop? So there's some before that there's some key terms that I was mentioning in the previous slide. Now eigenvalues is nothing but the square of some distances of the data points. So whatever data points we had in the original sense, what is their sum of squared distance from the origin or from the mean. So either way, if you have standardized the data, your mean will be 0. So that's why I was saying from the 0 point. Now eigenvector is a singular vector representing the direction, also the loadings that is there. So let's say a particular vector represents 4 or 5 columns. The values within them or the loadings within them as I was showing in the previous slide, the values within them is basically the losing is the weight that it gives to each column that was there in the data. So that's how we have to interpret what a vector is. And the loading is, as I was mentioning, is the weight given by a component to each column that was there in the non-reduced data set. Now, key plots, the one which I'm showing right now is called a scree plot, and you can even do a histogram plot as well. Now, whenever you are running PCA, you also need to understand the variance that a P component explains. So if you do a covariance of PC1, it will give you some certain value, PC2, PC3. And if you feel like that 80 to 85% of variance is explained by your component one, then that is also sufficient for you to run your further analysis or build a model top of it. You can even build a cumulative variance plot, which is nothing but a scree plot, and you can take it up to the level of 100%, but it is always advisable that you can keep up to two components or three components, where as and when you are passing the 80% percent threshold for your components. Few quick tips around PCA, as I've been keep talking about it. You always have to standardize your data. There cannot be any null values across columns or rows when you're running this exercise. And there has to be no outlier, because your component could be biased toward one of the data point that is skewing your data. So that is something that you need to always take care of while running this exercise. Moving forward in factor analysis, it is nothing but an extension of PCA only. It is there we were talking about matrix multiplication and how we decompose a matrix to get this out of it. Here the approach is slightly simpler, but also it can also be solved through a matrix approach. You can assume a linear equation in your head, and each data point or each column could be part of a linear equation. So if you, for an example, let's assume a movie data set that consists of columns like rating, likes, type, genre, theme, views. And if I have to, let's say, run a factor analysis of it, it would give me an output something like collaborates fields like likes, view, and ratings, and I can interpret that as something called an engagement of that particular row or that particular movie for this data points were there. And theme, genre, and length of the movie could be something related to movie characteristic or a movie type that were collaborated together with factor analysis. So with factor analysis, what we can interpret is we tend to collaborate or combine the variables that hint towards a similar thing or a similar or are pointing towards a similar direction, and that is what it helps us in combining together. Now how it does is, you can imagine, let's say you had 100 columns in your data, you pick first 5 columns in your data, try to form a linear equation. In the first approach it won't be possible, but as you do this stepwise, the algorithm in factor analysis does this thing stepwise. So it picks the combination of variables, tries to see if there is a linear equation being able to fit, and how it does this is nothing but like a maximum likelihood approach that we also use in our linear regression or logistic regression. They try to attain that minimum point where the error is minimum, and if at that particular point you are able to generate a particular factor out of it, that is what is the goal of this particular thing. So again, an extension of this, but again, the difference is in PCA, all the variables in the original data set were combined together to form a P component one, or basically the component one had all the data points or all the information that was there in the initial set of variables in one component, whereas factors will not possess that. One factor could possess only information related to 2, 3 variables, where other factor could have for other uh, 3 variables. They are, when you are running a factor analysis, a good check is that your factors are not very correlated to each other. That is where, when you can say that all my factors are equally good, well created, and they are exhaustive from each other, and that is the one check that you should always be doing. Now, again, just like how there was a question in terms of determining the number of factors that are there. So just like this is an inverse way of scree plot, but we are doing the same approach. Even factor analysis will give you eigenvalues for all the factors that you create in your data. It will not be like that you have a factor created and you are not able to interpret it. And how do you know what could be the cutoff in it? So the best or a thumb rule in factor analysis or dimensionality reduction, like approaches like PC and factor analysis, that always keep features that have eigenvalues greater than 1, because they kind of possess the maximum information of your data. Now, to walk you through a particular example of factor analysis here, I took a data set which was a kind of a survey data and kind of wanted to understand what kind of factors are created and whether I'm able to interpret these factors or not. So if you're not able to interpret your factor, that means there has to be a redo of the exercise again, because usually factor analysis give you a good interpretable format where we can make some sense out of what data points or what columns you have in your data. Now, what you see here is a spider plot, and that is one of the key plots that you can also use when you're working around factor analysis or cluster analysis. It gives you a good sense of understanding that particular cluster or factor or component. So it's a good visualization approach that you can consider while running these kind of exercises. Now, when talking about this particular survey data, so I had questionnaire related to different kind of formats, and we all had to, like in that particular survey, everyone had to give a certain kind of score to each kind of metric. So based on the responses that were there in the survey, I kind of tried to run factor analysis to it. So one few set of variables that were there is workload score, whether the work is challenging or not, learning curve in the workspace, whether there is team support or not, and whether you are well informed about your work. Now, if you can see, this was one of the factor created out of it, and it grouped 5 variables for me. Obviously, the key variable out of it was learning curve, challenging work, and team support. So these were the three key variables that were driving this factor. So that's why I named it probably as something related to work-life balance. You are able to see team support, the work is not challenging. So something that hints towards a work-life balance. So that's how I will interpret this particular factor in the data. And whenever you're running a visualization or explaining it to your clients also, it is a good way of showing and understanding that particular factor. Then again, there was some set of features in the data that cater to probably wanted to understand how's the workspace, what kind of facilities are there any different activities, system and equipments. So it was only related to 4 attributes, and you can see I probably called it in the very layman term as probably a workplace score, that how a person sees his workplace. And that's how the factor also, or the algorithm also, understand that these kind of variables should be clubbed together. Because what you could see that these variables kind of follow a same direction. They might be correlated to each other, but not at a scale that we can drop one of them. But the direction in which they point, or the where they are hinting the entire algorithm, is the same direction. And actually, when you fit a linear equation, it tends to attain a maxima as well. So that's why we see these kind of variables are grouped together as well. There were other aspects to this particular survey where it asked about cultural diversity and workplace, whether there are strict rules or not, accessibility to people, different activities. Again, it's, and you can see there, this is one use case where the variables are not exhaustive, but we usually see they are mostly exhaustive and do not overlap. Here, the importance of different activities is come, whereas in this particular case, we see that it is getting a higher weightage towards it. And then inclusivity. So we could see that it is pointing at good variables and it has a lower score towards strict rules, but all of them, these variable kind of point at the same direction. Strict rule, like if a person is saying there is inclusivity and there are, we are accessible to people, then you might feel there are less kind of strict rules. So that's why it has less importance, or that's how the model has interpreted it. So this is one way of interpreting our factor analysis, and this is one kind of a visualization approach that you can either use in PCA as well, or any kind of cluster analysis that you tend to use, and it will give you a fair idea of how a factor looks like. When I talk about PCA for this kind of visualization, it might be very hard because it is made out of all the columns that are there. So then you will have to imagine probably a spider plot of more than 10 edges where you have all these columns there and it is pointing out to someone. So then you cannot give it a name, or you can tell that this component tells me this particular story only. So that kind of trade-off always exists when we are looking at this particular thing. Um, I'll probably take a pause and see if there are any questions. This question on how to standardize the data. So in terms of standardizing the data, we usually go by approach of subtracting each of your So there are multiple approach, min, max, scalar. I have spoken about it by last session. So there are multiple approach. You can scale your data between -1 to 1 or 0 to 1. But the basic funda around this is that you, for each data point, you subtract that with your mean and divide it by the total value of the data if you still feel the ranges is high. So this is this basic way of standardization of data that we do in day-to-day life. So there is no, the other question is around what number of features will require dimensionality reduction. So there is no size constraint um, to this particular thing. Whenever your dimension, like say you have more than numerical three columns and more than 10, 4 or 5 rows in your data, that means your data is already 4 cross 5 space. So that is something that you cannot visualize in a 2D plot. So the idea of PC or factor analysis is that you can visualize something in a 2D format. So whenever you go beyond that, there is always a scope of applying these techniques. But I would recommend that whenever you have more than 10, 12 variables and you can't make much sense out of those variables also in terms of what they interpret, what they infer, then is the right time that these kind of approaches should be applied on the data. Moving forward, I also have an example of PCN, and this also ties back to the question I was just answering. Let's say I'm taking a basic example of iris data set, which is widely available everywhere, and I've just taken a snapshot out of it. And you can see there are 4 numerical columns, 1 categorical column. Now, if I have to represent this column in a scatter plot, and I cannot do it in one visualization, I'll have to create all these 6 visualization that I've created. Basically, it is divided by categories, differentiated by categories. I have one axis for one particular column, other axis for one particular column, and the values represented in between is the third column. So I'll have to probably create 3 cross 2 combination to basically see how these categories vary with each other. Now, if I end up running principal component analysis on top of that, I will be able to represent in a 2D format. Now, this is what, when I ran PC on this particular data, this is what I got. I could see clear clusters getting created out of it, and I could see both the components easily able to help me visualize how these 3 categories are related to each other, whether they are converging or not. And if you imagine this for a huge set of data which has large set of columns in them, then it becomes a much better exercise. It gives you a much better representation. This was a very small data, and still that it is functional. But the best use cases or the best practice of these kind of PCA analysis is when you run it on a larger data set. Usually the best practices around, or the best use cases are built around image processing use cases and textual data, where you have thousands of columns. So whenever you resize an image into a numerical data format, or you transform into a numerical data format, let's say you have RGB values, you have different pixel values in different columns, that kind of data should always be compressed. And it's a widely used practice that PCA is the best use case for transforming an image data or reducing an image data to 2 3 columns, and then build a particular model on top of that. Similarly, when I talk about textual data, you have, let's say, a huge paragraph on which you create columns out of it, which the columns could be word, and the values within them is the number of count of those words were present in that particular document. Now, you cannot go through every word or n-grams, bigrams that you create from that data, but you will have to concise that into a format that tells you the story of entire paragraph. So the one way of doing that is again PC and factor analysis. I also want to touch base something on the difference, which is the best use case for factor analysis and which is the best use case for PC also. So when there is no issue around, or when there is no hunch around explaining what your components are, then it is always advisable that you go by PCA. And PCA is tend to be more sophisticated. Is built on a more better mathematical covariance approach or a decomposition approach, whereas factor analysis is built on a linear equation, fitting of a linear equation there. Now, fact sometimes that there can be cases, or this is one of the limitation of factor analysis, that some of the variables might not get captured in any of the columns. or any of the factors that are getting created. Now that is when that will happen only when that particular column is interpreting or directing you towards a different kind of value only, or different kind of information from the rest of the data set. So whenever you have such kind of use cases, PCA is the best approach because it tends to take information from every column and put it in one component. So whenever you feel like there is no scope of you to reduce information, no scope of information loss, there is no scope of reducing your number of variables, you need the information with you. PCA, I would say, is the better approach. Where a factor analysis, when you want to interpret what are the combination or factors getting created, then that is the approach that you should be looking at. No, so there is another question around PCA considering eigenvalues less than 1. So no, in both the cases, we are considering eigenvalues greater than 1. If you are getting confused with this is nothing but the loadings. So loading is the weight that a PCA component would give to each of the columns. So let's say there were k columns here. So you can imagine this as k rows now, and this is the loadings that is associated to it. So for each of the column there is a loading associated. And if you go back and check the eigenvalues that the vector will be having, it will be greater than 1 for each of the columns. So that is always a thumb rule. Either you're using factor analysis or principal component analysis. Yeah, so image classification I was mentioning is the best use case for PCA. Uh, that you always have to go with an approach of dimensionality reduction there. When you break down an image into a data set, there are the minimum column number of columns that I have seen getting created is around 1000, 2000, which captures for each pixel that is there. And if the image is of a very high quality, then the column number of columns also tend to increase. So there PCA works the best. It combines the pixels that tell you a particular information. It combines the pixel that, let's say, some color pixels of red are combined together, and you see that as a component out. Similarly, from factor analysis, you can do the same thing. But PCA is again important there because you don't want to have any information loss, where in factor analysis, dealing with an image classification data, you might tend to that the algorithm might tend to skip some columns that might not be fitting with any linear equation or part of any factor. So yeah, that's one good use case for PCA there. If there are no questions further, I think we can close the session. That's was more or less on the PC and factor analysis. We'll be bringing forward few more topics around data understanding, how we transform data, and then delving into the scope of how we enhance our models better. So PC and factor analysis is one of the two approaches, are the two approaches with which you can obviously enhance the performance of your models. It will reduce the computational time of your model as well. Okay, so there were certain questions on the chat as well. Let me go to them one by one. So dimensions are not same as column. Dimension is the dot, like the number of rows into number of columns. That would be dimension of your data. I have utilized TSNE, but again, it is based around a similar approach of clustering, and the representation comes out similar to PC. And you will, when you compare these two algorithms, you won't see much difference between TSNE and PCA. TSNE is obviously the more advanced approach of dealing with it. I think you've answered this question of PC and factor analysis. Yeah, so you can loadings, weightage are all the same things, which can help you like understand what a component is associated to. So if a component has, let's say you had k columns in your data set, and there will be loading associated to each of these column with respect to a column, that will help you understand which the component is preferring which column the most. So although it is a distributed weight that is given, and it's very hard to differentiate which column has more weighting, but it's a good way to understand what your component or what your factor is made of. So that's why the weight is important. So the last question is, can we do clustering if data is having variables? So PCA and factor analysis is nothing but a clustering approach that you not apply row wise but column wise. So that is the only difference. It's again an unsupervised way, like K means. Yes, Renuka. So that's it's a similar way. It's an unsupervised way, as you might saw that I was not talking about dependent variable at any stage. So along with the this deck material, I will be sharing what kind of Python packages, if someone works on R, what they can leverage, if someone works on Python, and I will try to share the GitHub links as well, which can help you understand and run across various use cases of PC and factor analysis, and you can give a shot at these. So yeah, I think with this we can close our session. Thank you for holding on throughout the session, and I hope you liked the content, and I hope we'll be connecting soon forward for more session around data analytics. Thanks a lot.